The first challenge that came into my work is the first stuff you need to do is to be able to model the attacks for making the detection both explicable, explainable, so that you get and the security operator get the suitable information for being able to understand what's going on and to react. Second, to be able to perform detection of complex multi-step attacks in system traces and sometimes in huge system traces. And the third challenge, which is one of the most interesting, how you can use all this algorithm to learn the new attacks so that you can adapt the analysis and you can prepare the reaction. And at each of these steps during my project's research, I always came to the same conclusion. There's one kind of representation of the system which is really promising and really useful. That is the graph format, and this is what I will introduce you today. Let me first introduce the running example that I will use through this presentation, the UNSW IoT botnet detection dataset, which is now a couple of years old because it was published in 2018, but nonetheless very representative of the different issues that we are interested: capability of scanning the system, capability of performing denial of service, but also capability of performing specific focused attacks, generating botnet, making specific reconnaissance work. This dataset is built representing some attackers. You have the target, which is the victim system, and through it you have command and control system, which leverages actually quite a lot of knowledge to inject in the scanners, in the loader of the system, and through a dedicated network of controlled, armed IoT system attacks the final victims. And this is what we'll use. Some information about this dataset. The dataset is quite heavily focused on malicious data, a lot of standard denial of service, but also quite a lot of reconnaissance and very focused theft operation, which are the ones that will also interest us a lot. The first research challenge I'm interested in the first stuff you need to do before you can learn the object. You need to be able to represent it, and representation in the domain of computer science is, of course, modeling our attacks, modeling the behavior. So remind you of the research challenge, research question one I want to address today with you is how you can model the attacks for an explainable and transferable detection process. One very promising candidate is a graph. What we want to do is to be able to extract suitable information so that we can extract the information about the behavior of the system, about the normal behavior of the system, about the machines which are available, as well as to be able to highlight, to extract the attack information so that it's possible to react quite quickly, and to empower the security operator to take actions. Which are the properties that you need in your systems to be able to empower these reactions? The first is you need transparency in the system, transparency in the learning, and transparency in the analysis. Second is you need that your system is able to enforce accountability, where the data come from, where the detection come from. And last and least, you need to support the human oversight so that you can provide a view of the system, a view of what's going on, so that you can both understand how the system is working in its normal way and how the attack is going on. And we have also to consider additional properties so to ensure the correct process of your data, that you need, of course, to enforce privacy. You need to enforce security, protect the detection system, protect the protection, to ensure the diversity of the data origin, and always keep in mind the societal impact of our detection. So let's come back to a bit of history now. The concept of attack graphs was first really formalized by Shiner in the beginning of the year 2000, and structured both as a representation of the different attacks and the different steps that occur are used inside an attack, but also that formalized as Bushy automata, so that you can process these steps and process its interaction automatically. Original objective of attack graph to identify where do the attacker enter into the system, how it can take the first step into the system here in the example using vulnerability, a buffer overflow in some web service here, IIS, and then from this first step go laterally here, perform a port scan, exploit remote access, remote to user access in the system, then exploit local buffer overflow issue inside a local system to be able to perform elevation of privilege and then get access to the target system, to the target data. Of course, in this process, you will have a lot of trigger for alarms in your intrusion detection system, and this forces the attacker to be able to identify alternate routes, alternate ways to enter a new system, to explore the system very, very deeply and very precisely, so as to be able to perform the attack in the alternative process, which is shown on the picture here on the right. Here we get formalism for attack representation. We get the expression of patterns for intrusion detection systems, and we get also a very fundamental capability of sharing the knowledge visually, which is very, very important for rather really early steps of attack graphs. But the first brick were really already defined. The limitation of this is the process of building the attack graph and deploying the probes, analyzing it is really tedious, really manual, really time costly, and very specific to the target system you are considering, and absolutely not transferable, which absolutely does not match what we need nowadays. The models have, of course, evolved a lot, just actually to encompass more data sources, more references, to perform some automation, to start to support heterogeneous systems, but it still relies a lot too much actually on expert knowledge, and really misses tools to support all that. So a very interesting tools, very powerful tools from the conceptual side, still not operational enough. So we have a very, very interesting brick here with attack graphs, but this is not sufficient. Let's see now an example on another data set that we use regularly, which is focused on IoT in the context of medical system, which is a virtual IBMS 2020 testbed, and show what an example of what we can expect from graph, and a very, very simple example, but very, very highlighting. In this scenario, we have two devices actually here, the laptop discussing with the server. So we have the laptop in 10.0.172 and sending messages to server in 10.0.150. And then at some moment comes the attacker, and what does he do? He wants to take the place of the data emitter, to fake the data. It takes the IP of the system, but he cannot hide his own on MAC address. So in the system, in the graph, the resulting graph, then we see that when we enhance the graph, means we need to change the graph, the graph model a bit to support MAC addresses. Means we need to have specific probes to support this MAC addresses, which are not always available. We can identify that this simple connection is actually duplicated. Somebody has the same address, but then at the different MAC address. So this highlights both the promise we can have from graph, and at the same time the difficulty that we need more data, we need more precise probes. Let's show you another example of we wanted to get human oversight through our detection system. And this is an example with our UNSW IoT botnet system, where we see that on one side we have one clean behavior with one server and IoT devices, and as well as a much more intricate part, which in red contain the main attack traces. So through the graph, we can also have the second promise that we will get a really visual perception of what the system is and how it's going. Of course, in this case we are dealing with forensics analysis, where we know already which attacks are highlighted. How we get to it will be the content of the next slide. So then, how do we get this information? This traffic, this information is not normal and not satisfactory. The first test we make, and the first idea was to use ranking of the nodes and to exploit graph level algorithm. We started with PageRank algorithm, which actually proves very useful and very efficient to extract attacks when the attacks are, let's say, simple ones, traffic, really visible in the traffic, like denial of services, like scan, and here, example of one tool that we develop in the team, where you really see how the abnormal traffic is really highlighted in red. So this brings us to our first very lightweight solution, and which is very useful for exploration. Of course, we are really limited to the main traffic information and information traffic rate, which is of course not sufficient. The second pattern we're dealing with is we wanted to be able to perform pattern extraction. The pattern still focus on the graph structural properties, but then look for more specific behaviors, one node talking to another, and then switching, or one to a second to a third one. So we have a series of patterns, considering also the properties of the individual nodes, the kind of IPs we have, the kind of MAC we have, like in the super spoofing example we saw. This enables to support attacks like man in the middle, hide on opening. Hide on opening means, as in the example, we talked about, you first get inside the system and then perform lateral Highland hops to access the real target of the attack. It is based on GQL language, request of GraphQL language request, and is very performant to identify low-hanging fruits, easy attacks, and what I call dangerous patterns, which are behavior which are not necessarily malicious, but which occur a lot in the case of malicious behavior. You will say, okay, how does it help that I see that something may be a problem? We'll see how we can use it in the learning process. On the left here, you see the overview of the whole network. identifying different attack patterns. And on the right, you identify, you see a zoom on one specific node, the 192.168.106, where we want really to study the behavior of one single node, and for which we list the attack, the potential problem that have been identified here. We have subject of scan, several UDP scans, several TCP scan, different route and from different machines. So this was about the first pattern. Once we have the pattern, actually we can really go one step beyond. The example I show you, we use it for forensics. So after the attack, once you extracted the attack information, then you can get you can look for specific behavior and check node per node, step by step, if the actual behavior matches an attack, or it's just some kind of dangerous looking behavior, but not a real threat. The next step we perform, and this we did with Julio Navarro, which is a PhD that I had under my direction, who defended his PhD in 2019. He took this attack graphs and transformed them into daemon detectors, and namely using stochastic approach, checking the graph. Do I have the first entry? So the first entry in my system. If I see the first entry for a specific attack, then I will look not for any traffic, but for the two next steps. So like let's say example for the intrusion using the web service is 0, then you can have either E1 or E2 that lead to the actual attack, maybe according to the configuration, to the versions of the server. You can either, if E2 is vulnerable, E2 server is vulnerable, then you can enter directly, or you need to go to a third party, and then you can conclude the attack by performing several operations that enables you to access the same data, or the same kind of attacks. Here you find the example of the WannaCry attack, which was launched against Ukraine in 2017, and highlighted the fact that at this moment a lot of enterprises, multinational enterprises, did not isolate correctly their Active Directory domain between the different countries. I guess in the meantime that are the lesson. So the first step is, you want of WannaCry, you have a successful HTTP request aiming at checking if I am in a virtual machine. So if somebody is trying to observe me as a malware, so I just stop, and then if I go to the while, if I'm in a real server, just go to the while and access the machines that does not exist, so I can go on. Then I connect to port TCP 445, and then perform, which is a SMB protocol, and then perform an SMB command to connect to this to the server. And for accessing this, we have different steps which enable which can be used as alternate step. And if you create this static attack graph and transform it into a live detector, then you can get really efficient. Really efficient detectors. The very interesting part in this model of this abstraction attack graph that extracted directly as abstraction from the traffic traces. This part is a bit manual, but really comes from the real traffic. It supports heterogeneous behavior of the attack, heterogeneous attack path, and is remarkably robust to describe the widespread schemas of advanced persistence threats, and very useful for forensic analysis, and here also for live detection of APTs, and proof really powerful. Some other examples of attack that we have been able to detect besides WannaCry attack, so the open attack here at the example for ESCX, 2012 intrusion detection evaluation data set where you have fast, you have intrusion like phishing with an email with attached exploit, and then from there get access to a reverse TCP shell and access to more powerful machines in the network until you get in the an interesting server. So several hubs. Another example of, which is actually really similar in the process with the one that we crafted in the context of the FUE UMA project with several steps. Each step was a bit more specific and more bound to the teaching objective that we see in the graph. Beside that, we have 1, 2, 3 steps that enables to perform these attacks, and that can be taken alternatively one or the other. And the benefit for that we can also deploy these graphs as attack scenario graph for runtime detection besides forensics. So we have really 2 use cases: forensics for post-mortem analysis and runtime detection to detect live what's going on currently. So this very interesting fast result was one of the main project we made around graph. Led us to analyze more deeply the structure of this graph, and we started with Message Jabber, who will present this work in CC conference next week in a talk. The analysis of spectra, to say how we can use not only the patterns, which are really specific for specific attacks and really rely heavily on knowledge, but more the structure of the graph, the structure of the interaction. To leverage what we expect from graphs is to be able to exploit the information of the interaction between the machine. And here we really focus on studying the graph spectra, the graph structure, and namely we are working very precisely on the behavior of eigenvalues of Laplacian matrix for the detection, which enables we are from big graph like that. You see we have some kind of star behavior with one central node and a lot of clients, 1, 2, 3, and a fourth star here, which is really more lightweight than the others. And in red, you see the malicious traffic. Second view of the data, and then a zoom and one specific behavior, and we find again this star behavior and interconnected graphs here, which are which show more complex behaviors. How we do want to leverage this information, the eigenvalues of the Laplacian matrix, actually realized one that we see, especially in IoT domain, we have very often this structure with central server and the nodes, and this is really one of the patterns that come very often, and that can come in several flavors. It can come so like a chain where you have a kind of distributed IoT network with several places and several hubs which gather the data of surrounding sensors, for instance, or you can have more tree structures like that. And what's really interesting is we can identify the number of the endpoint of the graph through the eigenvalue, and you can identify also the number of independent components of the structure, like on this plateau here. And of course, this are behavior that occur in real attack, and the work we are currently doing with Message Jabber on this work is how we can extract which are the information we need to extract the specific connections to highlight these attacks, and be able to extract this structural information to detect specific and low signal attacks. So this was the first challenge of my work, where we really want to reverse the wide scope of graph models from simple node ranking to structural patterns, then to define and attack scenarios first as patterns and as detectors, and lastly to go to use more advanced metric like metrics from the graph spectra to perform fine-grained graph structural analysis. So actually, the objective is really to use all kind of information, but in all these different steps, we see one main point which is very important. Graphs are very powerful for detecting punctual behaviors or really schematic structure, but you cannot directly make the binding between the presence of this structure, the presence of this suite of steps for asserting the presence of an attack. You learn a lot. This gives us a lot of hints, but is not sufficient to characterize actual cyber attacks. And this is where we come to detection on our work on detection, which deal with the issue of detecting complex multi-step attacks in big volume system traces. For that, I've given the example of IoT networks. We're also working with information system network and with core network system. What we will use, of course, there's a whole world of machine learning for cybersecurity. I would consider that the knowledge corpus is stable, whereas actually very few people master it, but the tools are more or less available. It starts to be deployed actually more as packed in the complete tools that rather than something which is really tunable, because it requires a lot of knowledge, both from the data science side and from the cybersecurity side. But actually, the main limitation of machine learning is when using machine learning for detecting attacks is exactly like I showed in this example. So always the running example of UNSW IoT botnet. Using the correct parameters, you can really identify and characterize and isolate the different kind of attacks. But you really only consider the feature of individual data points and not the interaction. It's like when you're dealing with machine learning for cybersecurity, it's just like the packets are totally independent one from the other. If they are somewhat similar to bad packets, malicious packets, or maybe they are malicious too, but you absolutely do not consider the interaction. You do not consider the connection between the machine, which is actually where the attacker go through. So we can gain a lot of information through machine learning, but we miss one fundamental issue. And in particular, you also really rely on machine learning to identify attacks that you know from past events, but not new events. So what are the key features of machine learning for cybersecurity that we also want to keep in our learning? We want to be able to have a good detection of good capability detection and being able to evaluate whether this detection is satisfactory. And so be very careful to use the right metrics here for comparing different attacks. Here there's a benchmark on different decision tree and decision forest algorithm, or XGBoost, historic gradient boosting, AdaBoost. Extra trees perform very nice bagging too. You see that random forest is a bit more poor, and here using a Matthews correlation coefficient is really suitable for unbalanced data. You need to be careful about that. The classical trade-offs between rate of false positive, rate of true positive with the RUC curve, or precision and recall trade-off with AU, PRC, curve is very important. So about detection performance, of course, the time performance is very important. We want to be able to deal with big data sets. So here we need to have scalable data sets. And here you say that this example here for this is for XGBoost. We see that we have a very good detection, but nonetheless we have a scalability which is this seems to be a bit more than linear. So the more the data, the more costly it comes. So if we have huge data set, then we can have a problem. And the times of scoring is also very important. And one element that we want to be able to look at, which are the features, which are the columns, which are the information, the kind of packets, the size of the packet, the protocols that are used, the flags of the network packet, and through there are a certain number of algorithms like XGBoost, for instance, where you can easily extract the importance of the individual features to be able to know where does this what the information come from. And here you see this feature, this here in a theoretical example, there for the numbers 7, 21, and 6. They are the feature that you need to consider as what are actually in this concrete example of IoT botnet, the 3 dimensions here, which are given, should be able to extract quite clearly the different attacks. So now that we have this baseline, we have the world of attack graph and the variation that we propose, and the world of machine learning, which provide powerful tools. There are 3 main outputs that we need to solve. The first is scalability. If you have a lot of data, then how can you identify the attacks? The second is performance. You need to be really to be quick. To perform the detection, and you have explainability, because we want to provide the security operators with the information they need to react, not only to say, okay, I know I have a problem, but to be able to react, to block the propagation of the attack, to isolate the victim machines, and to be able to recover very quickly. And all that in the context of environments which are really heterogeneous. This is all the more true in the context of IoT, but I mean, information systems, we have also different flavors of operating systems, networks, devices, and so on. You have the big problems about false positive, what is called alert flood. Even if you have a very small rate of false positive, then for the operator, if you have each warning out of 10, which is false, then you will take time to understand and to explore an attack, which is actually not an attack, but you will learn it later. So it's a very key problem. And beware of the implementation complexity of the algorithm, so that you have relevant algorithm and you have also solutions that you can tune according to your need. And when you are when you're in a hurry because you are under a cyber attack, you cannot take the time to hire more data scientists to start discovering your system. You really need to be able to perform a cybersecurity attack quickly. So three key issues that keep open: how we can consider the interaction between the node, how can we develop scalable solution, and how can we learn novel attacks. So the first element we want to work with on graph learning is to be able to consider the nodes in their environment. And for that, the solution is given by the embedding, which say, okay, for each node, I also consider the node, but also I consider the surrounding node and transform it on some kind of vector representing this environment, representing this the context of each node, so that we have an enriched data considering the nodes, considering the connection, but also considering the environment. Which are the embeddings which are used typically? Node-to-vec, graph stage, which are really actually tools for transforming nodes to vectors. Take the neighborhood into account, but there's one main limit which is that this very static approach. But nonetheless, it's a very powerful one. You need to consider the kind of strategy you use when exploiting the embedding. You can have so multi-op neighborhood sampling, so you want to go as far as possible, as far away from your from the keynote, or you have random structure, which make a process like depicted here and given in Mengia's survey. So you start from the graph, you extract the different works of your system, very often random works, and then encode through very often the skip graph model is used very often, and then extract the latent vector space. So thanks to that, we have a representation of our graph as a list of vector. So this is first step, but it's not sufficient. Once we have the vector, we have not yet performed the learning. So let's go back now a bit back in time, almost 20 years ago, where the really earlier works were proposed, even though the technology really found massive results in the last 2 to 3 years, namely graph neural networks. The idea is, we want to be able to take the connection of systems into account, and also to be able to identify to classify the nodes during the detection. For that, you need to take the graph, you transform it into a network where you see with two different types of nodes, F nodes and G nodes. F node takes the edges as input, and G nodes take the graph nodes as input. And this is a fast work to couple with graph structures and machine learning. It was done before. We get very efficient machine learning tools in the beginning of 2010s. Here. And it already proved very efficient on different kind of graph. And this problem, for instance, here on the click problem, neural version is each time more efficient. I mean, you get 5% benefits. It's not radical, but it's really an improvement. And again, with really prototypical neural network at the date. Let's see a bit more precisely what is the process that we need to take into account. So the first, we have the information, the traces, and we have this phase of graph learning layer. So graph learning is what we have seen both as the extraction of the graph and then the enrichment of this graph with embedding, with identification of patterns. So graph learning is a couple of the two issues, both the creation of the graph itself from the different network traces, and the enrichment of the graph, embedding, attack patterns, and network patterns, which makes we have a graph output layer, and through a convolution layer we can get a graph output, which enables to support or supervise and semi-dependent supervise detection. A graphical example here, using T30, which enables to isolate the different cluster represented in different categories, where you see kind of the approaches are very relevant for extracting and discriminating between the categories. The limitation of that process is very specific to each program. The graph learning, graph extraction, pattern extraction, as well as the convolution structure will be very different for each problem. Graph extraction adds an additional layer of complexity, and the graph learning layer is always very ad hoc. This is why we wanted to focus on some more specific properties, and namely the connectivity inside the graph. We first started to work with communities, community metric like density, externality. So density is how much the nodes inside one community are connected, and externality is how much the nodes between one community and another community are connected. These first metrics proved to improve quite significantly the detection, but was not sufficient. This is why we introduced two additional matrix, working with the dynamics, and considering the dynamics proves to be very performant. Namely, we define local stability as the similarity of one community between one time step and the other, and global stability is to say the stability integrated over the time. This solution focuses really on building a more advanced graph learning layer and using then after quite classical and performant machine learning algorithm. We see with the graph here in the middle that the performance is really good and tends to decrease in time when we have more data, and the time start to lower and not to increase, which is very important, and stabilize for the extraction for each individual point stabilizes, which is a very important, very good properties. And thanks to that, we made a complete benchmark, and we see here we use this version. So the first version is just using specific feature extraction with the baseline in blue, but first we define an advanced feature extraction, feature selection process, and hyperparameter tuning, so the classical approach for attack for machine learning, attack detection, and then we enrich it this process with this community metrics, and to manage to get here we talked about the MCC, which is very relevant for unbalanced data, to multiply by more than 2.5, 2.6 times the capability of detection through this optimized community matrix and this community metric dynamics. This shows that this using graph structure information is very relevant and provide a lot of information about the danger and the kind of attacks you have in the system. Of course, attack detection is not only a use case. Let me talk about the example work that was made by Vadis Ami in the team together with student Tristan Bilot last year for extracting define a complete GNN process for extracting phishing, identifying phishing side. Here is the representation of the graphs, and on the right you see the T30 representation before and after the processing. So we see we manage through GNN really to extract, to separate the malicious phishing traffic and normal, and with a very high and very performant result. And when compared with alternative approaches, really good fine-tuned solution. So this is our second step. So graph-based detection. We use embedding for neighbor exploration. We use feature extraction through graph metrics and graph-specific metrics for static communities, which already existed, but that we really evaluated, and for dynamic communities. And we use the capability of graph neural networks for scaling the detection. So here, the very good news that we have a radical accuracy gain, but the process remains very manual. And this leads us to learning. Then we'll show you a couple of examples how we can improve the learning, how we can learn new attacks to adapt analysis and prepare reaction in a way which is as much as possible automated. Let's go back to the work of Julian Navarro and the attack detectors, the daemon detectors. What we made with these daemon detectors is we presented the result. Instead of just presenting the result to an expert, we presented the result to an expert and enabled the expert to say, okay, this is an attack, or this looks like kind of an attack, but actually this not. So we can give feedbacks, and using anti-colony optimization-based approach pheromones, we get very interesting result that we can continue increase the detection rate, like here on the left. When we increase the probability of detection, we also keep on reducing the probability of false alarm, which is very important. Whereas if you do not have this feedback, then if you want to have too much detection to too big precision, then the recall really goes down, and you get a lot of false alarm. For that, we have a stochastic process, and it enables us to push the border of noiseless detection, improve precision while keeping recall, good recall, and fully relies on feedback and human operator. So the approach needs to be integrated in specific tools. So the next step is one to be able to autonomously learn. And here there's an example of isolation forest, because isolation forest is an unsupervised algorithm. So the first experiment we made, we could identify the attack, which was really managed with normal traffic, which was absolutely not satisfactory. But by identifying, performing suitable feature extraction, adding this the graph metric, like density and graph dynamics metric, we managed to have a quite great improve in the isolation capability of the process, and using the isolation forest, isolation score, as well as the stability metric. So we have a criteria that enables us to filter beyond the detection capability, to filter out the false positives, and to keep true positive only, while decreasing the alert flood. So as a conclusion, we've built capability for graph extraction and enrichment, capability for learning, and capability to get feedback. This gives us transparency, where the expert has all the information he needs about the attacks and where the attack come from. It keeps the oversight both visually and through the graph information, and the feedback enables to ensure accountability. Through the graph, we see where the attack comes from, which are the features which are concerned, which are the features which are relevant for the attack, and which are meaningful and semantically loaded. And sure, the challenge that must be kept into mind is how to keep the privacy, because we have a high transparency, and how to secure all this process. So for learning novel attacks, we use graph through reinforcement, through human feedback, through unsupervised learning, through discriminating features, and false positive prediction through suitable scoring. These models prove that this is a necessary and very efficient step toward explainable attack detection on a heterogeneous network. Of course, not sufficient. Other conclusions are in the history of detection. The work on intrusion detection system really started with decision trees quite a long time ago, with the first model used in the 1980s, then shifted to machine learning. Here at the example of KDD99, the classes, which is really old data set, but which has a really interesting continuum of data, and really challenging for the algorithm and for detection when not considering specific patterns, and to the graph learning, which really answer to really more recent requirements that were not covered by previous approach. Thanks to this graph, so we want to achieve scalability, performance, and explainability in our detection, support heterogeneous environment, cyber-physical environment, IoT environment, as well as IT environments, and to reuse as much as possible false positive and the alert flood. And of course, all this work also intends to standardize the different bricks that we use for learning, so to reduce the complexity of implementation for the end users. So thanks to all for your attention, and so I guess it's time for questions.
Okay, thanks a lot, Pierre, for the very cool presentation. I enjoyed it a lot, and it was a very different topic from what we had before, and at the same time very related. And let me start with pushing a little bit more this relation. So you also do non-graph-based cybersecurity research, cybersecurity works. So how is the link between the two? How was your journey towards these graph-based mechanisms for detection or improvement of cybersecurity?
Yeah, I came to working on graph actually through a really iterated project, because before I really realized that the model was maybe in itself a research object on the world of cybersecurity. The very first work that I've not presented here, because it's more related to the analysis of software itself, is during my PhD. I worked on system hardening and detection of vulnerabilities, and through point-to analysis, and the way that the information flows or can be accessed inside a software. And here there are, of course, quite a lot of good practices and models on the architectural side, but also models for defining dependencies between software components on the one side, and analysis of the code itself inside, where of course you have graph where you go from one place in the memory to the other, and then at some moment you get some information that the end user should not have access to. So this was the really first encounter I had with the concept of graph, and then the next I went on about system security, and then learning and detection, and to different kind of algorithm optimization of cybersecurity system through genetic algorithm, and then when exploring the stochastic approaches using genetic algorithm and colony optimization. So we realize that if you want to be able to optimize the rate of detection, optimize the capability of detection, what you do is always you optimize path. A bit like when you do traveling salesman problem, so you find the minimum path between a lot of towns. Here we wanted also to make the most secure system, and then again we had the different points, and then we needed to have the link to how you go to one point, one step of the process to the next, and to the next. And so was the example that I showed with the work of Julio Navarro, and starting with this idea of optimizing the learning, then we necessarily came to build the graph for optimizing the work through this graph. Yeah.
Okay, cool. Yeah, very, very nice. Yeah, so then I give over to Loic, and as always, I will kick in a little bit during the questions. So yeah, Loic, the floor is yours. You're still mute, I guess.
Yeah. That's better.
Perfect.
Yeah, okay. Yeah. Hi, Pierre. Thanks for the presentation.
Hello.
We have quite a few questions here in the Slido, so I guess I'll just pick them one by one and go.
Please do.
So first one, did you consider using other structures like stream graphs or link streams instead of just simple graphs to better capture the structural features and temporal features of the attacks?
Yes, actually, there's something that we still need to consider to have more advanced behavior. The first element we want to consider that is actually currently not covered by not really by the literature and absolutely not by the solutions. I mean, they are work, but we have no solution. It's fast to encounter just the connections. And actually, in the when working with on this work of Julio, how you extract the pattern that I showed, it's actually we have not made a formal comparison with stream graphs, and I think probably it should be a next step which would be very interesting and probably very rich. But we came to extracting the scenarios through time windows and extracting the different steps and the different session of the users from one machine to the other to the other. And I'm really convinced that it could be very powerful to use the formalism of stream graphs and stuff like that to represent that, but we have not gone so far yet.
Okay. Yeah. It's I agree with what you said. I guess it's since you talked about sampling, like to get the temporal features and structural features better of the graph, it's like also an alternative that could be used. So another question: how do you measure the trust into a graph?
Yeah, this is this is a really good question. So the question there are actually two level. When you talk about trust, it's a bit the overall question of trust in artificial intelligence, which means actually you have this European framework telling that there's European-wide there are some kind of tasks that actually have no impact whatsoever. So you need to have trust. If you have a game, you can just put any algorithm and your car just works around. It's not a problem. On the one hand, and on the other hand is everything that is like social measurement, which is really a taboo in Europe, and it's just not to be done. And for the others, you have two levels. You have all the application where you have impact on people, but you just need a bit of transparency, like when you create chatbot of stuff like that. You need to know where the data come from, and you need to answer which kind of answer you give to avoid that you take decision. For instance, if you have a medical chatbot, that you do not take decisions instead of medical people. But for that, just a bit of transparency is sufficient. And then you have this level of critical systems, which deals with into critical infrastructure decision, critical infrastructures. Instead of cybersecurity, you think of medicine. Or actually, the issue is very easy, I would say, is you cannot take automated decision, but you need to make all the information available to a human operator, so that the human operator can take first is expertise, and secondly is responsibility for taking the decision. And this brings to the question of explainability. So the question of how you measure trust is, for me, you have the list of criteria that I put here. You need to have human oversight, you have to have explainability, you need to have accountability. But actually, if you want to measure it, you need to be able to measure explainability. And so far, I would say shortly, there's no way to measure explainability. I mean, there are metrics, but the metrics are not enough understood so that their quantity is actually matching some intuitive values that you can use. These are work that you are doing with Amani, Aburida, and how to formalize the measure of explainability. And this is really ongoing work. But you're right. This is something which is really parallel. And the question is, to measure, there are some metrics, but the real question is how you make sense of the measure. This is a really open question.
Oh, Mop, you want to say something? I think you're muted.
Sorry, yeah, thanks. Yeah, I wanted to say, so the trust for me is especially also something when you look at a graph, you have something that is quite abstract from the raw data. And that means you have quite some distance between what you measured and what you present to the user. And trust is also how can you give the person looking at the graph a feeling of confidence? Okay, what I see here is really what I want to see. And related to that, as you said, machine learning can play an important role in the pipeline of processing. What is the impact regarding the trust of having machine learning in that pipeline?
Yeah, exactly. And the issue, what I really believe that graph can bring a lot is that since you have a lot more traceability with regard to individual nodes, individual edges in graph model that you have in standard machine learning model that are much more black box. So the issue is how you ensure the traceability to the events that trigger the alert, and how you ensure the traceability to the data set that trigger the alert. And when working with attack detection, this is one of the big challenge. We work with different kind of data sets according to the kind of use case. But one thing is common is that all the attacks we have are actually really quite absurdly schematic in the data sets themselves, because you have sometimes you have this kind of IPs with specific protocol settings for banning traffic, and then you have other kind of RPs with other kind of protocol parameters which have nothing to do with the attacks. So it's really tricky to learn, and this is very important to track.
Okay, cool. Back to Loic.
Yeah, just before just continuing on the question, I had one myself, because last week I was at cyber school where there was a presentation by Sébastien Gamps on synergies and tension between privacy and other issues in machine learning. And he was saying there's a basic conflict between, for example, privacy and fairness in machine learning. So I guess my question is, how do you feel those tensions between all those dimensions affect your work?
Yeah, this is a very important question, because if we want trust, we need traceability, and if you have traceability, you know who did what, and so you have no privacy. And so yeah, this is also one of the challenge with these models is how you can make federated learning, because federated learning basically relies on the fact that we use black box models. You have data in, and then you have some model out, and this model, is able to decide this is an attack. I mean, at least according to the previous data, and this is not an attack. But I do not tell you where I have the information from, and this is very positive for federated learning. But you're losing trust and you're losing explainability. If you have transparency, then you have no privacy anymore. So the question is how you can hide the structure of the actual identity of the providers, or you can hide the structure of the network, so that you can share the detectors without sharing information about the original IT system. And yeah, this is really two stuff which are perfectly opposite, at least in the current state of the art. And I would really completely agree with this privacy versus fairness.
And I guess even if you just share the models and not the network, you can still maybe guess some information about the network from the model. So it's not, it's perfect. So yeah, I'll pick another question. This one is a fun one. How is ChatGPT used for attacks?
Actually, so far, for us to make it short, I've not yet tested ChatGPT for performing cybersecurity attacks. So I will just answer from what I followed from the community. So far, I mean, ChatGPT is very good at building small pieces of code, so for specific systems that are well known. So you can craft and gain huge time for building exploit and building specific codes for very simple cases. On the one hand, and what is identified so far is the case I evoked, is that it would be essentially used for generating false email, phishing, for fake website stories, and stuff that seems consistent, text that seem consistent. So for cyber criminality, more than cyber attacks. As for me, actually, I would think that when you are dealing with a real attack on a real system, which is a bit complex and a bit specific, this is exactly the case where ChatGPT is totally dead. Because he is unable to do two stuff, is unable to work with two specific systems. As far as you have a technology that is not documented enough, or where you need two specific stuff, ChatGPT is just out, and is absolutely not good at integrating the stuff. And for me, these are the two challenges. So I would say, usually improving the productivity of attackers on very bounded tasks, generating phishing, we can assume that very quickly it will be possible if you have very specific, well-defined processes to make individual bricks for ChatGPT, so you can automate everything and make stuff that seems impressing, but to perform real attacks, I really think this is something that will still be very manual, as exactly as the counter attacks. So blue teaming and reverse engineering, for sure, the stuff that there are tasks that will be hugely accelerated, but others that will just be just keep very manual.
Mm-hmm. And to comment on that, so the as we looked at ChatGPT also a bit in the series, so I fully agree to you, and to reformulate it, so ChatGPT will make it much easier to do mainstream attacks. While before you had to buy some kits kits with a team in order to build something together, you still needed some knowledge about it, and now you can put it into a prompt and say like, okay, I want to attack this and that system. Maybe you can even find these systems if you have ChatGPT with connection to the real internet, and then it will craft you something that before needed at least some expertise in order to do it, and therefore the cybersecurity becomes even more important, because if you have a mainstream system, what many companies are, then it's now even more likely that more people have access to attack such kinds of systems. Okay, good. Yeah, but I just wanted to comment that. So back to you, Loic.
Yeah, no worries. One question that is really upvoted is, I guess you already partly answered this, but when are graphs helping for explainability? When are they self-explanatory?
So if to understand the question, there would be two cases. When there was parts where they are self-explanatory, and parts when there would be just help. I mean, for me, it depends on the aggregation tool that you use. When you have patterns which actually match themselves or specific points and entries, then you have such self-explanatory structures, because you have no machine 1 and this action is machine 2. In the case when you have more structural analysis, which for me is very promising, but you aggregate the information. So you consider, okay, here I see that inside some kind of graph star structure, or here I see some evolution in the community. So they will help a lot. I've showed how we can really almost multiply by 3 the performance of the detection for hard problems. But of course, you do not have you have just metrics on the community, and not telling which are the nodes which comes in and which comes out.
Okay. Next.
Or maybe to jump in there once again. Sorry for that. So the explainability question. This is also a graph that can also be something that is complex, because you have lots of data that is reduced to some two-dimensional or three-dimensional, depending on your visualization system thing. And therefore, the second part of the question was like, when is it self-explanatory? So did you, as you're doing research in that direction for quite a while, did you encounter some good practices towards having understandable graphs, or do they make it even more complicated in some cases? Can you share a little bit something your experience with that?
Could you complete a bit your question? It seems not so clear.
So you have the raw data, and then you do pre-processing, and then you have a graph. And this graph might be this node picture with the connectivity or something like that. And my question is, our goal is to reduce complexity. So we want that the analyst or the one who is doing cybersecurity that can more easily grasp something. And my question is rather, is it sometimes the case that it's better to look at the raw data because the graph is more complicated? Do you have some best practices on this is how you can make a graph less complicated? There's a good mapping between the data and the graph.
The issue we get with complexity is if you have too much node, then just visualization can become tricky for the tools and computing capability. But for the you have actually two main steps that are very important. The first is just being able to visualize, and here there's something that starts to be emerging in some mainstream tools, but still in a very limited way, to be able to visualize the interaction, to visualize the traffic. So basically, to recreate the architecture of the systems, but from the not from some specification, but from what actually happens. But we just understand the network is really the first benefit that we can have. And then after when you process the graph, when you say okay, here we have this behavior, of course, it's very important to be able to say which is the original trace, original packet. Let's say telling okay, we have the community number 27 that does this and this and that has which derivative is in this and this direction. I mean, if we must really be careful not to focus to abstract graph structural metrics. Otherwise, we lose a lot. And this is what occurs actually in almost all the papers on GNN for detection. I mean, you have no information. You have a really nice work on the GNN itself, really nice work on the process, really nice work on the performance of the everything. But we have lost in this work almost all traces. Or yes, look, we detected this attacks because we aggregate the graph so much, and so for me the GNNs are very dangerous for that. They are quite powerful. They can exploit more information, but sometimes, at least in the way they are used or they are researched currently, we totally lose the binding. In the case of cybersecurity, it's very obvious, but for other use cases too. Sorry, it's a really good point, really good question.
Mm-hmm. Okay, thank you very much. So with that, I hand over to Erkin if I correctly understood the chat.
Yeah. So I will take over for the, I guess, remaining questions. Professor Parra, let me start with my question.
Yeah.
Less than a month ago, a group of people, including some rich businessmen like Elon Musk, but as well as some serious, accomplished professors, Joshua Bengio, Stuart Russell, signed a petition, an open letter, for pausing giant AI experiments, at least for 6 months.
Yeah.
What do you think of this letter, if you had a chance to read, or in general, a threat coming from this powerful AIs, maybe even more powerful than GPT-4? What are your comments on that?
Yeah, my first reaction Which when you first I mean there's I'm really convinced that everybody has in mind that maybe one day we can have we can have application that suddenly enable to change to change the way we can behave with the system, or the way we can behave between people very differently, so that the risk exists that one day we cannot control anymore the machines we have. And this is an open question, and this when this would happen, actually there's a lot of people playing crystal balls, but nobody has any idea. And also the question is more, what for me is first, what could be the risk? And I mean, everybody say, okay, it's dangerous, but what are the risk, and how we deal with the risk? And I think as cyber security community, we probably have a role to play to say, okay, let's keep our head a bit cold, identify what are the problems, and identify if what are the signs that we would consider that we are come to a point that is dangerous, or not, and how we can react. I mean, we already with ChatGPT we already see radical impacts. I think most of us who are researchers are also teachers. Since January, it's not possible anymore to give any kind of homework to any student. And so we have a radical change in our job. But I mean, it is an existential risk to human being. I'm not so sure. But for individually, for our different job, it can change, and we can also think that for some kind of people, then this could sweeten the job. This is on the one hand. So the identifying risk is the first issue. The second, about this latter, or we need to start to stop. I would say, okay, if we stop, I mean the only it's what we say, something, the promises only engage the people listening to the promises. If we stop, the only people that will stop is the people who are naive enough to think that if they stop, the others will stop too. I mean, I mean, I cannot imagine that Elon Musk is actually someone who's really pragmatic and do not seem so much concerned with. I mean, at least humanism, as other people defend, is much more to having result and technical result. I cannot imagine that he would stop making any experiment because somebody signed a paper somewhere. And I mean, there's no reason that Chinese competitor stop because Joshua Bengio signs a paper. And I do not see Microsoft or Facebook or Google or Amazon, to say the big West firms, taking 6 months lag against their Chinese competitor, which start to be very powerful, to have more data and more engineers, at least as skilled as the US firms. I mean, this makes no sense. That the big US firms would stop, and I really just maybe they try to slow down naive people, but I do not know who.
So so as Akin was kicking really fundamental questions, let me also jump in there. So if I understood it correctly, it was rather that the public usage of the tooling would be stopped for 6 months, and the development would continue in the background.
Yeah.
But I also find it totally unrealistic. Elon Musk, or first of all, in November, we'll have one person from Microsoft who is working in a close relation with the ChatGPT. So this will be very interesting in the November edition of this discussion. But besides that, Elon Musk is always very AI threat putting. He's always like, okay, it's already too late. The thing is out, and we are all living in an AI, and it's really dangerous. Personally, I would say I was just reading yesterday. I think there was this news that the Sony Photography Award was won by a person that was using DALL-E, so the image generator of the OpenAI, and he won this global photography award. And this is quite interesting to me because it's really the Turing test in the sense. Someone submitted a photo, a jury of photographers and of people decided that this is the best photo that is taken. And therefore, I would say the threat potential is really in, we have mediated reality. And for people having this trust relationship, so is this real or is it not real? I think, so to me, this would be the big threat.
Yeah, exactly.
Okay, good. But that just as a comment, and back to Erkin.
My next question, Professor PARREND, how do you research? What is a key for a successful research? Besides hardworking, we know that. I mean, of course, this is something I hear a lot from Professor Pal as well. Of course, we have to work a lot, but what is key for a successful research besides working?
Yeah, what I say, you can have depend on which level you position yourself. As a lab, we have a lot of audits, so we all need to keep in mind the different audit criteria, and this always give a lot of milestones. That's to say, okay, publishing is of course always something which is very important, and the direction that we currently take as a community is going more towards high quality, meaning high bibliometry research, which has advantages but also drawbacks. Software becomes more and more important as research deliverable, including libraries, tools, and reproducible papers, and data is very important. So I would say as guideline, it is really take making useful predictions for the community. Depending on the exact topic of what you are working on, will make the strengths more on one or the other. But I would say what's important for qualitative research is to be able to contribute these three elements to the community. And for me, the question of bibliography and bibliometry is quite important because on the one hand, we are all urged to publish in good papers, but we also absolutely need not to forget to make the communities live. And there are a lot of very small, local or very focused community where you can have a lot of very qualitative discussions, a lot more of creativity, and more than in very formal event of processes. So I'm really convinced we must not forget the creativity part to also be able to come in with new ideas, risky ideas, and not only stuff that are this year expected by the evaluators.
Thank you very much, Professor Parra. I guess
thank you for your questions.
Our time is also almost up, so I hand over back to Professor Pal.
Okay, yeah, thank you very much, Erkin and Loic, for the wonderful question moderation, as always, and also for your own questions. If you have a super quick answer, I would ask you that, but really say something super quick. So, to me, when I was studying this graph-based approaches for cybersecurity, it was totally underrepresented, so I didn't have much courses about that. Do you offer such courses? What would be in these courses? Which courses should I take if I'm interested in such methodology?
Very good question. So far, I have not seen comprehensive courses. We will soon have students that work on this in the EPITA because we have artificial intelligence with graph major that has just opened. and I've one of the students in my team has by chance joined this major, so I will be able to tell you more in 6 months. But currently, and I'm even not sure we put a specific cybersecurity module in it. I think this really is something that still needs to be crafted.
Okay, cool. And it could also be something for this mini module for the MOOC I was talking to you about for October, because I consider the topic even hyper interesting, because it's complementary to not complementary, but it's a different direction to the 3D analysis that we also have had in the series already, because this is more immersive doing something, and it uses more traditional in quotation marks, but at the same time it's also still a vast research field, because it's not that the holy grail is found and we have the best visualizations.
And it binds very innovative stuff with the latest graph results that have emerged in the last 2-3 years, together with the historical approach of the attack graphs that are quite widely used for 20 or 30 years.
Yeah. Okay, cool. That said, as again already said very well, the time is unluckily already up. So thanks again, Pierre. It was really a very insightful and wonderful talk. We also had quite some of your students participating in the discussions. Also, thanks a lot for that, and a lot for the audience questions. The next edition will be on the 31st of May. It will be with Ludovic May, who is the Deputy Scientific Director of INRIA. And I will show you the picture in a second, and the trailer will also be online shortly. So thanks again, everybody, for participating. Stay, as always, safe and cyber secure. Tell the people about the series so that we have even more audience the next time. Subscribe on the website to the invitations and on the channel for the videos. Thanks again, Pierre, and keep safe. See you all very soon. Bye-bye.
Thanks. Bye-bye. Bye-bye to all.
Cher cyber-CNI, pôle d'excellence région Bretagne. Au revoir et à la prochaine.